Okay, now we're going to be ready to do 3.8, to be determined. This is another develop understanding task, which means 3.8 is the start of a new idea. Let's get started. Israel and Miriam are working together on a homework assignment. They need to write the equations of quadratic functions from the information given in a table or a graph. At first, this work seemed really easy. However, as they continued to work on the assignment, the algebra got more challenging and raised some interesting questions that they can't wait to ask their teacher. Work through the following problems from Israel and Miriam's homework. Use the information in the table or the graph to write the equation of the quadratic function in all three forms. You may start with any form you choose, but you need to find all three equivalent forms. If you get stuck, your teacher has some hints from Israel and Miriam that might help you. Okay. So let's look at question 1 and see if we can't write a form here. Immediately, I'm drawn to where the x-intercepts are and where the vertex is. So I see the vertex is here, and that looks like -3, -1. Oh, excuse me, -2, -1. So this would be the vertex. I also see that there's a point here at -1, 0, and another point here at -3, 0. So from this, I can tell a couple of things. I can tell that there is no dilation, or that the dilation is 1, right? It hasn't been stretched or compressed. I can tell that because if I move 1 away from the vertex, I'm going up by 1. And that's a sign that there's no dilation. Because I know the vertex, I can immediately go to vertex form and write y equals x plus 2 squared minus 1. And that doesn't have an a value. It doesn't have a dilation value here because, like we said, there was no dilation. The factored form we can write from the x-intercepts. We know there's an x-intercept at -3 and another one at -1. So we can write y equals x plus 3 and x plus 1. And then for the standard form equation, we can either multiply this out, or we can multiply this out and subtract 1. In my mind, I know how to do this very quickly. I'm going to do x squared plus 4x plus 4 minus 1, which is x squared plus 4x plus 3. And I also noticed that 3 is the y-intercept, which matches here. Okay, let's do question 2. Okay, immediately I see the vertex is here. And I see that my y-intercepts, or I mean my x-intercepts here and here, do not have integer values. I'm going to look for where it crosses properly. It looks like there's a point here and here, which tells me again that there's no dilation. And it looks like there's a point here as well and here as well. So the vertex is -2, -2. For vertex form, we can write y equals x plus 2 squared minus 2. For standard form, we can just multiply this out and subtract 2. And give us x squared plus 4x plus 2. Now for factored form, it's going to be a little tricky. We need to find those x-intercepts. So let's find the x-intercepts using vertex form, and then we can reverse engineer factored form. So let's find the x-intercepts. We're going to set an equation where this is equal to 0. And that means that whatever x we find, that'll be our x-intercept. We can add 2. Take the square root of both sides. Plus minus square root of 2 equals x plus 2. and then we can subtract 2. So we get minus 2 plus or minus the square root of 2. So these are our x-intercepts. There's an x-intercept at -2 plus square root of 2, and there's an x-intercept at -2 minus square root of 2. So in factor form, we subtract those. So we're going to have x minus -2 plus square root of 2, and x minus -2 minus square root of 2. And so that would be our factored form. Okay, let's go to question 3. Okay, again, I noticed a vertex here, and that's at -2, 0, and I see that here as well. That's also the x-intercept. So since it only has one x-intercept, that probably means that it has 2 x-intercepts and they're the same. So and let's take a look to see at the growth if it's dilated at all. It doesn't look like it. So our vertex form is going to be f of x equals no dilation, x minus 2 squared, and no addition or subtraction because there's no translation there. For standard form, it's going to be f of x equals x squared plus 4x, or excuse me, this should be minus 4x minus 4, or plus 4. I think I made a mistake somewhere. The vertex is -2, 0. That means this should be plus 2. This should be plus 4. Okay. Now, if I factor this, I get 2 factors of the same amount, the same binomial. So f of x equals x plus 2 times x plus 2. Okay. This one has a vertex here, and the vertex is at -2, 1, and I see that here. This is the vertex. Does it still follow? It does. So there's no dilation. So we can write y equals x plus 2 squared plus 1. If I multiply this out, I can get our standard form, y equals x squared plus 4x plus 4 plus 1, which would be plus 5. Now the factor form, if I can't really factor this, but I know that if I get the x-intercepts, that I can write the x-intercepts, I can reverse engineer factor form. So let's do that. Let's set this equal to 0. Subtract 1 from both sides. Square root both sides. Subtract 2 from both sides. Okay, so this is our x, and these are both of our x-intercepts. We have one where it's -2 plus the square root of -1 and -2 minus the square root of -1. So we can write our factor form, x minus -2 plus square root of -1 and x minus -2 minus square root of -1. That would be our factored form. Now, there should be a problem here because what's the square root of -1? We don't have an answer for that. And we'll talk about that here in a second. Let's read question 5. Israel was concerned that his factored form for the function in question 4 didn't look quite right. He thinks this doesn't look right. Miriam suggested that he test it out by plugging in some values for x to see if he gets the same points as those in the table. Test your factored form. Do you get the same values as those in the table? Okay, so we can plug in a couple of different points and see if we get the same ones as the table. So let's plug in -2. We're going to plug in -2 here and here. So I'm just going to copy this, and instead of x, I'm going to put -2. -2 minus -2 plus square root of -1 -2 minus -2 minus square root of -1. Okay, we can distribute this negative sign here and here and here and here. -2 plus 2 minus square root of -1. -2 plus 2 plus square root of -1. If I add these together, that's going to be 0. That's going to be 0. So I get negative square root of -1 and positive square root of -1. Well, okay, negative times positive is negative. And the square root of -1, we don't know what that is. There's not a number for that. But we do know that usually if you have two square roots of the same number and you multiply them together, you get the number inside. Like, for example, if I had like square root of 3 times square root of 3, we know that that would be 3. So square root of -1 times square root of -1, that would be -1. And -1 is 1. So the number I plugged in was -2, and the answer I got was 1. That actually matches with the table right here. Plugged in -2, I got 1 for the vertex. So this factored form does work. You just have to kind of know what to do with these square roots of -1. Why might Israel be concerned about writing the factor form of the function in question 4? Square root of -1 is not a real number. This number does not exist. How can you have a number times itself and it equals -1? Okay, let's keep going. Here are some more from Israel and Miriam's homework. So let's do this one. Here we have a point there. It looks like we have a point here and here. We see that it's pointing down, and we see that there's no dilation other than that. So we can write y equals x plus 2 squared plus 2, and it's negative. The factored form we don't have because we can't tell those here, but we can tell the standard form. If we multiply this out, we get x squared plus 4x plus 4, which is negative. So we get negative x squared plus minus 4x minus 4, and then plus 2. So y equals negative x squared minus 4x minus 2. And then the factored form, we're going to have to solve this and then plug it, remake our factored form. So let's solve it. Negative x plus 2 squared plus 2. Subtract 2 from both sides. Divide both sides by -1. Square root both sides. And subtract 2 from both sides. So these are our two x-intercepts. We can write them in factored form. X minus. We can put a number here and here. And this was going to be -2 plus root 2. This was going to be -2 minus root 2. Okay. Then let's do the next one here. We've got a vertex there. Again, there's no dilation. And it's just pointing up. So this vertex form is going to be y equals x plus 2 squared plus 2, no negatives. The standard form is going to be y equals x squared plus 4x plus 6. And then to find the factor form, we're going to need to solve this. So we get 0 equals x plus 2 squared plus 2, subtract 2 from both sides. Take the square root of both sides. Subtract 2 from both sides. Okay, and we get this. It looks very similar to the one we had up here, doesn't it? It looks very similar. So our factor form is going to be similar as well. X minus -2 plus the square root of -2. And x minus -2 minus the square root of -2. Miriam notices that the graphs of function 7 and function 8 have the same vertex point. Israel notices that the graphs of function 2 and function 7 are mirror images across the x-axis. What do you notice about the roots of these three quadratic functions? They're pretty much identical if you look at the roots, right? So look at these roots here and those roots here. They're very similar solutions, very similar roots. The only difference is this one is the square root of -2 and this one's the square root of 2. So they have the same vertex and their solutions look very similar. Solutions look similar. For example, -2 plus square root of 2 versus -2 plus square root of -2. Okay, let's keep going. The fundamental theorem of algebra. A polynomial function is a function of the form y equals a sub 0 x to the n power plus a sub 1 x to the n minus 1 power plus a sub 2 x to the n minus 2 power plus ... so on and so on until a to the n, a sub n, where all the exponents are positive integers and all the coefficients are constants. As the theory of finding roots of polynomial functions evolved, a 17th century mathematician, Girard, made the following claim, which has come to be known as the fundamental theorem of algebra. An nth degree polynomial function has nth roots. Okay. So this is a little bit of history. In later math classes, you will study polynomial functions that contain higher order terms, such as x to the third power or x to the fifth power. Based on your work in this task, do you believe this theorem holds for quadratic functions? That is, do all functions of the form y equals ax squared plus bx plus c always have two roots? Examine the graphs of each of the quadratic functions you have written equations for in the task. Do they all have two roots? Why or why not? Okay. Well, so in other words, does every equation that's quadratic have two solutions? Well, most of them have two x-intercepts. The ones that don't have two x-intercepts, like this one, you can still write it in factored form with two different factors. And when you solve it, you still get two different solutions. Even this one, which only had, this was number 3, which only had one x-intercept. It only touched the x-axis once. When you factored it, you got two factors, even though they were repeated. So, is it true that a quadratic function always has two solutions, even though sometimes those solutions are the same or they might look weird? Yes. So, do they all have two roots? Yes. They all have two roots. Okay, why? Why do they all have two roots? It's because they're all squared. And whenever you solve a squared, you always end up with a square root. And the square root always has a plus or minus, which means you always end up with two of them. So when solving squared terms, we take the square root which always gives two solutions. That's one way to explain it. There's a couple of other ways, but that's the way I'm choosing to explain it now. Okay, let's do some ready, set, goes. Simplify each of the radicals below. Okay, square root of 8. That's the same as the square root of 4 times the square root of 2. And the square root of 4 is 2. That's that. Square root of 18 is the square root of 9 times the square root of 2. And that's 3 root 2. The square root of 32 That's the same as the square root of 16 times the square root of 2, which is 4 root 2. Okay, the square root of 20, that's the same as the square root of 4 times the square root of 5. And the square root of 4 is 2. So this would be 2 root 5. 45. That's the same as the square root of 9 times the square root of 5, which is 3 root 5. 80. 80 is the same as the square root of 16 times the square root of 5, and that is 4 root 5. What is the connection between the radicals above? They all follow the same pattern. It's 2 root something, 3 root something, 4 root something. This one had like square root of 4. This one always had square root of 9. This one always had square root of 16. Okay. Here's the set. Determine the nature of the x-intercepts for each quadratic below. Given the quadratic function, its graph, or other information below, determine the nature of the x-intercepts. Is it a whole number? Is it integer, rational, irrational, or not real? Okay, well, these x-intercepts cross here and here. Those are both integers. So I'm going to put the fancy z that it shows here. Both of these are integers. These x-intercepts are, there are no x-intercepts, so it's not real. Not real. They capitalize real. Okay, let's look some more. Determine the nature of the x-intercepts. Can I factor this? 24 is 12 times 2, 4 times 6, 8 times 3. It's not factorable. It is not factorable, which means that this is going to be irrational. So that's the Q with the little line over it. I'm going to write off to the side because it looks like I underlined the 24. It's the Q with the line over it. Because I couldn't factor it. If I could factor it, then it would either be integers or it would be rational, meaning they would be fractions. Because we can factor fractions, we can factor integers, but when we can't factor it, we know that there's going to be like a square root somewhere, and so that's why it's irrational. Like this one, see, it's factored, but these are fraction answers, right? This would be 1/2, this would be -2/5. So these ones are rational. That's the Q without the line. You can have fractions. Okay, let's see. In here, we have one that crosses properly, and this one does not. Can I factor this? Can I factor this? It looks, so that's -1, or that's crossing at 1. Can I factor this into x minus 1 and x, something should be 2x minus 5 plus 5? Does that work? Five minus 2. Yeah, that works. So these are rational as well. Yeah, this multiplies out to give you that. Determine the nature of these x-intercepts. The graph doesn't even cross the x-axis, so this is not real. Those x-intercepts are not real. Okay, what about here? Can I factor this? Yes, this factors into t minus 4 and t minus 4. These are whole numbers. We're going to use a w. Because both of those would be at 4. Determine the nature of the x-intercepts here. Ooh, can I factor this one? Let's see. Two numbers that multiply to 27 and add up to -5. 9 and 3 are the only numbers that multiply to 27, and they do not add up to -5. I don't think that this is factorable. Since it's not factorable, I think the answer is that these, well, what if they're not real though? Let me think. If I try to put this in vertex form, I could do negative b over 2a. So the line of symmetry is 5 over 6. That's the line of symmetry. And if I multiplied that over here, square it, that gives you 25 over 36. And you would need to add that times 3. I'm trying to determine where the vertex is here. So I know that the vertex is 5, 6. 5/6. But I don't know the y value. Let's use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times c. That's 4 times 3 is 12 times 9 is 108 over 2 times 3. 25 minus 108 is negative 83, I think. The square root is a negative number, and we don't have a number that times itself that gives us a negative number, right? Because negative times negative is positive, and positive times positive is positive. So there's not an answer to this. Therefore, the answer is that it's not real. Oh, that was a tricky one. Okay, so that one's not real. Determine the number of roots that each polynomial will have. Okay, based on what we learned, it's based on whatever's the highest exponent. So this one has a 5, this one has 5 roots. This one has a 3, this one's going to have 3 roots. This one has a 7, so it'll have 7 roots. And I'm looking here, here, and here. That tells you how many solutions it's going to have. Okay, let's do the go. If the quadratic function can be factored, then factor and provide the x-intercepts. If you cannot factor the function, then use the quadratic formula to find the x-intercepts. Okay, let's do this. So numbers that multiply to 21 are 7 and 3, which I can get 4. So this is going to be x plus 7 and x minus 3. And give the x-intercepts. The x-intercepts are going to be negative 7, 0 and 3, 0. Okay. Can this one be factored? Two numbers that multiply to 15 and adds up to 16. It's 5 and 1. So we can do 5x squared plus 15x plus x plus 3. Factor out the 5x here. We get x plus 3. Factor out 1 here. 5x plus 1 times x plus 3. Our x-intercepts are going to be negative 3, 0 and negative 1/5, 0. Okay, let's go to 21. Two numbers that multiply to 1. Okay, this one you can't factor it, so let's use the quadratic formula. Negative b, it's excuse me, x equals negative b plus or minus the square root of b squared minus 4 times a times c, which is 4, over 2 times a, which is 2. 4 plus or minus the square root of 12, and the square root of 12 is 2 root 3. So we can write this as 4 plus or minus 2 square root 3 over 2, or 2 plus or minus the square root of 3, because the 2 will reduce. Yeah, so. And you can write those as points. 2 plus root 3 comma 0, 2 minus root 3 comma 0. Okay, 22. Same deal, we're going to need quadratic formula. X equals negative b plus or minus the square root of b squared, 256, minus 4 times a times c, which is minus 16, over 2 times 1, which is just 2. So that's going to be 16 plus or minus the square root of 240 over 2. 240 has 4 in it, and that would equal 16. 240 has 10 times 24. Let me think about 240. 240 has 10 and 24, which is 6 and 4 and 5 and 2. 6 has 3 and 2. So there's 2 2s and a 4 in there. So there's a 16 and leftovers are 5 and 3. So that's going to equal 16 plus or minus 4 root 15 over 2, which is 8 plus or minus 2 root 15. For 22. Okay, 23. Two numbers that multiply to negative 40 and add up to 3. You've got 20 and 2, 4 and 10, 8 and 5, 8 and 5. That's the one. X plus 8, x minus 5. So the answers are x can equal negative 8, x can equal 5. Okay, let's look here. Two numbers that multiply to 18 adds up to 3. 3 and 6. We can do 2x squared minus 6x plus 3x minus 9. Factor out 2x here. We get x minus 3. Factor out 3 here. We get x minus 3. And we get 2x plus 3 and x minus 3. So our solutions are that x can equal 3 or x can equal negative 3 over 2. Okay, over here, number 25, this one's super easy to factor. You can just factor x, and that gives you x times x minus 3. So x can equal 0 or x can equal 3. 4 and 2, x plus 4 and x plus 2. So x can equal negative 4 and x can equal negative 2. Quadratic formula for this one. It says we need to use the quadratic formula. Otherwise, I would try to solve this a different way. But we can use the quadratic formula here. The middle term is missing. We don't have an x. So that means b is 0. So x equals 0 plus or minus the square root of 0 squared minus 4 times 3, which is 12, times negative 11. 4 times 3 is 12. 12, that's 132, negative 132, over 2 times a, which is 6. So x equals plus or minus 132, like I said, is 12 and 11, and 12 has a 4 and a 3 in it. So we can say 2 root 33 over 6, and the 2 reduces with the 6. And that gives us square root of 33 over 3. All right. That is the end of task 3.8. I'll see you next time for task 3.9. As always, make sure that you check with your teacher, ask questions, and make sure that you spend time understanding the work instead of just copying it down. All right, see you then.